Welcome back to another exciting adventure of Mr. Wernau Does Your Homework. Alright, so I'm just gonna go over a few of these questions on this little worksheet right here. We're gonna review some series tests, and of course the first one, of course, there's a sequence. So we're just gonna review a couple of these. This is 9.1 through 9.4. Basically, it's gonna be sequences through limit comparison, direct and limit comparison. Alright, so let's take a look at question number 1 right here. For question number 1, it says, does the following sequence converge or diverge? So we might remember what we're really looking for is, what this is really saying is, as n goes to infinity, will we reach a number? Will we reach, or I guess a better way to say it, will we approach a constant, or just some number? So we do that by just taking the limit. We take the limit as n goes to infinity. And we might remember with factorials, what we're going to do with factorials to make these a little bit easier for us to solve these, we're going to expand the bigger one. And n plus 1 is bigger than n minus 1. So if we expand it, we're going to get n plus 1 times n minus 1. And once I get to the n minus 1, notice they're both s on the bottom as well. And I'm not going to expand any further, so I'll just leave that as n minus 1 factorial. And I just put that over the n minus 1 factorial, and those cancel. And of course, now we're just left with the limit as n goes to infinity of n plus 1 times n, which as n goes to infinity here, this just becomes infinity. Now notice, this is not a constant, this is diverging. So therefore, the sequence here diverges. This is not really a test. It's not a test. It's just sequence diverges. This is not a series. Alright, so let's review some series type of questions real quickly. Question number 2 down here. We want to know if this converges or diverges. Remember to include all work and include your test used. So your answer should have the following. 1, does the series diverge or converge? And 2, what test did you use for this? AP is not going to accept just guesswork, so you really always want to put down which test you're using. So for the first one, you might recognize this as geometric, and if you did, you're really good. That makes it really easy. So my geometric just says if I look at the magnitude of r, which is going to be 1/3 here, it's less than 1. And my rule for geometric says because that's less than 1, my values are going to be shrinking as we go on. My terms are going to decrease over time. And according to a geometric series, that means this is going to converge. So we can say, therefore, the series converges by the geometric series test. The geometric series test. Remember, 2 things you're going to be looking for. 1, your work, and when you write your answer, does the series converge or diverge, and what test are you using? Now, number 3 always gets people always they don't really necessarily like this one very much. So, but I'm going to go over an old school, old trick that we can use. Since I have a common denominator, I can split my fraction here. And that's what we're going to do here. So we're looking at the series as n goes from 1 to infinity, 2 plus 3 to the n over 5 to the n. I'm going to split my fraction. And in doing so, we're going to get 2 series. The first series is going to be 2 over 5 to the n, and the second one is 3 to the n over 5 to the n. And maybe we can recognize a little bit here. We saw this in the notes in another video. If I have 2 over 5 to the n, that's really saying 2 times 1/5 to the n right there. Plus, and of course these both have an n, so I can just write them out. I can factor them out. And if you notice, these are both geometric series. For the first one, the magnitude of r is equal to 1/5, which is less than 1. And the second one, the magnitude of r is 3/5, also less than 1. So these both converge. Both of these series converge by geometric series. So we're going to say that, so the whole thing must converge. Therefore, the series converges by the geometric series test right there. And there we have it. You can abbreviate a little bit. Now, the question students will ask, well, what if this was bigger than 1? What instead of saying 1/5, this was 7/5? Well, if this were 7/5, this would be greater than 1, and this part would diverge. But take a look. I'm taking something that diverges and I'm adding it to something that does converge. Well, while this is going to infinity, this stops. So the whole series would also diverge as well. So if one of them diverges, the whole thing must diverge as well. All right, number 4, just because it's kind of fun. All right, so this is not geometric, so I am going to go to my next one, which is most likely the nth term, and I'm going to check that. The nth term, you might remember, what we're looking for is, does the term not equal 0? As we go to infinity, we don't want this to equal 0. And of course this doesn't. This is my horizontal asymptote. Of course you can use L'Hopital's. And we get 1 right here, which does not equal 0. Well, remember what this says, as n approaches infinity, we are adding 1 forever. So this will have to diverge. As n gets really large, what I'm going to wind up at the end is just adding plus 1, plus 1, plus 1, plus 1 forever. It's very similar to my sequence, right? Remember, if my sequence, this is basically my sequence here will converge to 1. But remember, the sum is I'm adding all of those ones together, so forever. So this will diverge. So therefore, the series here diverges by nth term. Very easy to do these. All right, let's take a look at number 5 right here. Now, number 5, if I take a look here, if I try the nth term, I'm going to try. It's not geometric, but if I try the nth term, I get 1 over n, I get 0, which means the nth term fails. So we have to think of another way to do this. Now, of course, we have the integral test, which for the integral test for this one is really complex. It's really too hard for it. We don't like the integral test all that much. But I noticed, this sets in my p series. We had a video on that earlier, where my power here is 1. Why we call it the p series. So we know p is 1. And because of this, we know that this series must diverge. That's our p series. If you do the integral test, you can prove that using the integral test. So therefore, the series diverges by p series. And since now the other way we can do it, instead of using p series, we can recognize this as harmonic, or the series is harmonic, therefore diverges. If you can recognize that too. Both of these are acceptable by the AP and everything else. Alright, so let's try a few more of these, but let's go on down to question number 9 down here. Now, question number 9, this is not geometric, and nth term will give me 0. We can hopefully see that, because if I did nth term, the bottom is going a lot faster than the top, so that's going to become 0. So nth term fails, geometric fails. My other choice is I can use the integral test, but the integral test for this one just seems a little bit overkill for it. So I'm not really interested in doing the integral test on a problem like number 9. So the next one I'm going to go to is my comparison. So when we do our direct comparison, I'm going to let a sub n be the original function, n over 5n squared minus 4. And my b sub n, well, what really matters as n gets really large, this is just really n over 5 to the n squared, which just becomes 1 over 5n. And this is my comparison right here. So when I do my comparison, that's part 1, we're going to do the comparison. When I look at n equals 1 to infinity, I'm going to check this 1 over 5 to the n. And again, this is a power series. P is 1. Therefore, this series right here diverges by P series. We're not done, because now we have to check it. And you might recall from the other video and the other lesson, when you check this, you want to make sure that a sub n is greater than b sub n. You want to make, because if this diverges, And you want to make sure that a sub n is bigger than it. Because if a sub n, if my original is bigger than my comparison, and my comparison diverges, my original must also diverge. And that's going to be true here. If we take n over 5n squared minus 4, that's going to be bigger than 1 over 5n. So it works. May not be in the short run, but in the long run is really what we're looking for there. So because this is true, we will now say the series diverges by direct comparison. And there's our answer right there. Very easy to do. Alright, similar to that one, we got number 11. So let's take a look at number 11 right here. Now again, I could probably use direct comparison, but doggone it, does that look nasty. I'm not even going to try any of the other one. I am automatically, when I see something like this, I'm thinking limit comparison. So there's my a sub n. My b sub n would be what really matters, the 3n on top and the n cubed on bottom, which just becomes 3 over, of course, that becomes n squared right there. And if we try this one, when we compare this one, the comparison part, n equals 1 to infinity, we're going to get 3 over n squared. And again, this is a p series. P is 2, and that means that this is going to diverge. And you can check that by using, this will converge by p series test. So we will say this series converges by p series. So now we have to do the limit part of it. And the limit part, remember, it said the limit as, what do we got here? As n goes to infinity, a sub n over b sub n. And I'm going to do a little bit of algebra here to simplify this. This becomes 3n minus 2 over n cubed minus 2n squared plus 11 times, and I'm going to flip that, n squared over 3. Now, using a little bit of algebra right here, I can do a little bit of algebra right here, and this just becomes 3n cubed over 3n cubed, so this just becomes 3 over 3, which is 1, which is finite and positive. So, therefore, this series converges by limit comparison. All right. And of course you can try these. And number 10 you will most likely have to use nth term, but you're going to be using L'Hopital's there. The last one I want to take a look at here is number 15 here with you. All right. Number 15 says use the integral test for this one, and then would direct comparison work? I'll let you guys figure that one out. So let's use the integral test. For the integral test, we're going to let f of x equal our function 1 over x square root natural log of x. Now, f of x is positive, continuous, and decreasing as n gets really large. So that tells me we can use the integral test. So therefore, when we take the integral from 1 to infinity, 1 over x natural log of root natural log of x dx. Don't forget this is improper, so we do have to write it. The limit as b goes to infinity, 1 to b, 1 over x root natural log of x dx. And integrating here, we're going to use u substitution. U is natural log of x. Du is 1 over x dx, and dx is x du. Now, of course, those x's will cancel, and what we're left with is the limit as b goes to infinity, and this becomes the integral 1 over root u du. And when we write this out, we get the limit as b goes to infinity. This becomes 2 root u, which is just natural log of x, and we evaluate that from 1 to b. And solving this one, we get the limit as b goes to infinity, and this becomes 2 times the natural log of b minus, and if you plug in the 1, that just becomes 0. Let b go to infinity, and we get the integral diverges. The integral diverges. Cancel diverges. Now, if the integral diverges, what does that mean about the the limit. Remember, the integral and the limit go hand in hand. Therefore, we can say that the that the series diverges by the integral test. This is why we don't like the integral test. Look at this one. It's the longest one, the most writing you'll ever do in your life. Look at that. It's crazy. All right, I hope you enjoyed these videos. I will see you all later. Bye-bye.